In this example, I will refer you to the extreme value theorem that says if f is continuous on a closed interval of x values from a to b, then there's going to exist x values c and d on that closed interval from a to b, such that f of c will give you an absolute max and f of d will give you an absolute min. Now here are two functions, f and g, in this sketch that each satisfy the hypothesis of the extreme value theorem. You can see the one on the left, it's defined on a closed interval from a to b, and as is the picture on the right. And both of these graphs, graph f and graph g, are continuous. You can imagine an ant walking on them. They're never going to fall through any holes or fall off any cliffs. They're continuous on the closed interval of x values from a to b. Okay, so they do meet the criterion of this function, this theorem. Now we can clearly see in the graph the results of this extreme value theorem, and that is specifically that both of these graphs have absolute maximum at x equals c. That's what I'm going to mark it as, x equals c. Well, b is c in this example, and c is next to b, a little less in this example. Those are absolute maximums, and then they both have absolute minimums at x equals d. Where's d? D is the minimum on the first graph here and on the second graph here. And they could have more than one of these each. It's just in this example they just have one. Here's a little sketch of what it might look like if there's more than one minimum. We have this function on a closed interval, continuous, and we see I just circled the two minimum points and the one maximum point. Okay, so the point is here that it met the criterion of the extreme value theorem. It was continuous. The function was continuous on a closed interval. So it included the endpoints in the graph. And then we knew for sure there would be an absolute maximum and an absolute minimum.